This is my Calculus 1 course. Today we're going to learn how to find volumes of solids of revolution. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. As usual, you're going to need these differentiation formulas, so if you don't have those memorized, take a picture. In previous classes, we learned that if f of x represents the heights of rectangles, then the definite integral of f of x gives us a number that represents the area of a region. Today we're going to learn that if a of x represents the areas of cross-sections of a solid, then the definite integral of a of x gives us a number that represents the volume of a solid. And we're going to start by learning the disk method, which is a way to understand why the definite integral of a function representing the area of cross-sections of a solid gives us the volume of a solid. So this is the disk method, but let's do an example to help us understand. If this area here is the area bounded by the red graph and the purple graphs and the x-axis, and we rotate that area about the x-axis, we get what we call a solid of revolution. And you can see that this solid kind of looks like a cup that's laying on its side. If this were the surface that it's laying on, you could see it's a cup. And we're going to learn how to find the volume of this shape here. Now, the cross section of that shape is a circle, as you can see here. If you cut straight down into the cup, parallel to the top of the cup, the cross section that is it's a two-dimensional shape, and it's a circle, that green circle. The area of the circle is pi r squared. Remember, if you want to find the area of a circle, you have to multiply pi times the radius squared, and that gives you the area. And the radius of each one of those cross sections is r. You see r over here. So r is the y value of this point xy, but the y value of the point is also called f of x. So the volume of this solid is given by the definite integral of the area of each cross section, which is pi r squared, and we can replace r with f of x. F of x is just this green length up here. And remember, this graph, this red graph up here, that's given to us by graphing f of x. So that's why that length is just f of x, and so we just have to find the value of this definite integral, and that gives us the volume of the solid. But obviously people want to know, well, why is that? Why does the definite integral of the cross-sectional area give us volume? And we could come up with a rigorous proof, but you're not really required to know how to do a rigorous proof of this. But mathematicians do like to ponder why this is. And so what they do is they try to come up with an explanation that relates what we did earlier in the course. We found the sum of the areas of an infinite number of rectangles, and we were able to find the exact area, the yellow area, under a curve. Well, what we're doing here is we're finding the sum of the volumes of an infinite number of disks. We call these disks. So up here we had a two-dimensional cross-section. This green circle is two-dimensional. But what if we give each cross-section a little bit of width? So let's say we have a green cross-section, but that cross-section only has two dimensions because it's just a circle, right? But what if we take it and add a little bit of width so it actually becomes a cylinder? So this blue part is the side of the cylinder, and the face of the cylinder is this, I guess I'll color it gray. Then we can find the volume of this using our volume formula for a cylinder. A disk is basically a cylinder. So we're going to find the volume of this cylinder, and we're going to we're going to think about a bunch of different cylinders fitting into this solid. And as we increase the number of cylinders, i.e. disks, our volume approximation gets better and better. So we're going to allow the number of disks or cylinders to approach infinity, and then the sum of the volumes of all those disks is going to be equal to the actual volume of this overall cup. And so that's how mathematicians think of this. So you can look this over if you want, but that's the concepts that mathematicians use to try to explain why the definite integral of the cross-sectional area of solids of revolution give us the volume of the solid. So let's do a practice problem. Again, you really don't need to know it in any more detail than that. You're not really required to understand it beyond that. But here's an example. It says find the volume of the solid generated by rotating the area bounded by x equals 2, x equals 4, y equals 0, and y equals root x about the x-axis. So we're going to find the region bounded by these curves, and we have that drawn there in yellow. And then we're going to rotate that area about the x-axis, and you see we create this cup shape. And so the volume of that cup shape is equal to the integral from 2 to 4, x equals 2 to x equals 4, of the cross-sectional area of the cup shape. So what is the cross-section? Well, again, if you cut this in the middle or anywhere, you get a circle shape. That's the cross-section is a circle shape. Again, a cross-section is a two-dimensional shape that you get when you cut straight down into a solid. And so these are circles. So the area of a circle is pi r squared. So pi times r squared. But what is r? Well, r is just the distance from the x-axis to this red graph. But that's just root x. Choose any point on that red graph. The x value is just x, and the y value is root x. So the y values are all root x, but that's the radius of the cross-section circles. So again, if you flip this over, you see when we rotate and create our solid, the radius of each cross-section is root x. So we plug in root x, and of course we have to square that because the area of a circle is pi r squared. So then we find our answer, and then we're done. So that was pretty easy. squaring the square root of x just does the opposite, so it just gets rid of the square root. And what I'm going to do is I'm going to pull out that pi out of the integral. And the reason I can do that is because it's a factor of what's inside the integral, a constant factor. As long as our factor is a constant, we can pull it out of the integral, but it has to be common to all of the terms in the integral. Now in this case we only have one term, so but because we're pulling out the constant, we have to write two brackets because we're multiplying pi by everything, whereas if we didn't pull out pi, we'd only have to write one bracket. So now we're going to plug in 4, and then we're going to plug in 2 and subtract these values. And so we get pi times 8 minus 2, which of course is 6. So our answer is 6 pi. And let me find a little more room. So our final answer is that's the volume of this cup shape. So that's how this works. Again, the problem tells us to find the area bounded by these graphs, and then we rotate it about the x-axis, and then we find the volume of that corresponding solid. Alright, so let's try another problem. Same type of problem. It says find the volume of the solid generated by rotating the graphs of these equations about the x-axis. So we have the area enclosed by those graphs, and if we rotate about the x-axis, we get this shape here, which I guess it kind of looks like a horn or something. Now notice in the previous example, our area that was enclosed started above the x-axis. It was above the x-axis and we rotated it around. Well, now our area is below the x-axis and we're going to rotate it around. But as long as you're integrating from left to right, meaning from negative 2.5 to 0, then you're still going to get a positive volume. You don't have to worry about your volume being negative. So let's find the volume. It's going to be the integral of the cross-sectional area. From negative 2.5 to 0. And the cross sections, they're just circles, so they're going to be pi r squared. And maybe I should have written pi r squared just so you can see that we're finding the or we're using the area of circles. I'll just write that extra thing in there so we know what exactly we're doing. So the integral from 2 to 4 pi r squared. This is the previous problem. So what is r? Well, r is just it's the equation of the red graph. It's just 1/8 x cubed, and you have to square it because that's the radius. Okay, now in the previous problem we took this pi out of the integral, but I'm going to keep it inside just so you know that you don't have to take it outside if you don't want. I prefer to take the constant, the GCFs, out of the integral because it makes it easier to do the problem. You don't have to write so many things. But I'm going to keep it in this time. So we have 1 over 64 times x to the 6th power dx. So if you're having trouble raising this green expression to the 2nd power, then that suggests that there's a problem, because this is calculus and you're expected to know basic exponent rules, your calculus teacher generally is not going to show you how to do that. So if you want to know the exponent rules, you can go to my intermediate algebra course. I believe I have 4 classes on the exponent rules, and you can review those. But we used exponent rule number 3 and exponent rule number 5. And I guess technically we used exponent rule number 4. But anyway, we can write pi over 64 times x to the 6th. And then we're going to find the antiderivative. That's going to be this expression here. And let me find some more room. So we're going to plug in 0. I think that's going to be 448 when we multiply. And it's probably going to be best to use our calculators here. So you can enter this into your calculator, and you should get 4.28 approximately. It's okay to use your calculator for some of these problems because the math gets pretty messy. So 4.28 is the volume of that horn shape thing that we created by rotating the area bounded by these graphs about the x-axis. Now again, notice we got a positive number. It doesn't matter if the area starts below the x-axis or above the x-axis. When you rotate it and integrate from left to right, it has to be left to right, then you get a positive number. If you integrate from right to left, you'll get a negative number. Same number, but it'll be negative. So now let's do a problem set. It says to find the volume of the solid generated by rotating the area bounded by the graphs of each set of equations about the x-axis. So we're doing the same thing that we did before. But notice that we don't have graphs of these equations. It's highly recommended that you graph the equations in order to see the area that you're considering. Maybe we should say the area that we're rotating, because we're really rotating the area. In most problems, you're not going to be given pictures like this. You're going to have to figure out what these pictures look like. So another thing that you're going to be expected to know, most students don't know this, but you're expected to know the library of relations and the library of functions, which we covered in my intermediate algebra course, but it's been a while since we went over that stuff. You're also going to be required to know how to transform parent graphs. And the reason that stuff is useful is what we're about to do now. If you know how to use transformations and you know your parent graphs and your parent relations and functions, then you can graph equations very quickly. But if you don't have if you're not familiar with that stuff, then this is going to take a lot longer. So I'm going to give you a picture of the library of relations, you can, again, this is all in my intermediate algebra course. So relations and transformations are something you need to review in order to be able to graph these equations. So I'm going to graph 1 over x minus 1. Now this is the reciprocal relation. So that means that there's horizontal asymptotes on the x and y axes. But we have this -1 here. So what do? Well, we have to do a transformation. So what we're going to do is we're going to add 1 to both sides, and now we can see that this equation, which is the same as this equation, is just moving the graph down 1 unit. Whenever you add something to y or x, you move to the left or down. If you subtract something from y or x, you move to the right or up. So we need to move this line downwards, this dotted line here. We need to move it down 1 unit. And we also have an asymptote on the x-axis. So let's graph this. I'm going to use orange, I guess. Actually, I think I'm going to stick with red. So our graph looks something like that. And I'm also going to graph y equals 0. And I'm going to graph x equals 2 and x equals 3. So x equals 2 is something like this. This graph does not have to be perfect. It just has to give you an idea of what area we're rotating. So now you can see that the area that we're considering is this area, this yellow area in here, and we're going to rotate that about the x-axis. So that gives us a shape that kind of looks like this. My graph isn't exactly accurate, but we're rotating and we're getting that shape. So it's kind of a little cup shape, and the cross-sectional areas are circles. And so we're going to use the disk method to find the volume of that shape. We're going to integrate from 2 to 3. We're going to integrate the cross-section area, and the cross-section area is pi r squared. And the radius of each circle is this distance. It's this distance here, which is 1 minus x over 1. So we have 1 over x minus 1. We have to square that because that's the radius. So we're adding up all of the disks, and the radius of each disk is 1 over x minus 1. Okay, so we're going to have to use FOIL, and I'm going to take the pi out of the integral. So we're going to multiply 1 over x minus 1 times 1 over x minus 1. And we're going to multiply the first terms, which are these blue terms. 1 over x times 1 over x is 1 over x squared. So if you're having trouble multiplying fractions, then that suggests that you're in the wrong course. That's just basic stuff. Your calculus teacher is not going to show you how to multiply fractions. But remember, if you have some fraction a over b times c over d, then you just multiply a and c and divide by, or multiply a and c and then multiply b and d, and that's your fraction. Again, that's basic stuff. Your calculus teacher is not going to show you that. So if you're having trouble with that, that's a serious issue. So these fractions have a common denominator, so we can add them up, and we get 2 over x. And we can't really integrate 1 over x squared very easily, so we're going to change to x to the negative 2 power. And we're also going to factor out that 2 so we can see that we have the 1 over x expression. So now we're ready to find the antiderivative. So So again, because we have the pi outside, we're going to need two brackets, not just one. We're going to add 1 to the exponent to find the antiderivative. Now the antiderivative of 1 over x, that's natural log x. Do you remember that? That's natural log x, and the antiderivative of 1 is just x. And our limits of integration are 2, 3. Okay, so we don't know how to deal with that expression there, so we have to convert it to negative 1 over x. And now we're ready to plug in our numbers. So we have negative 1/3 minus 2 times natural log 3 plus 3 minus negative 1/2 minus 2 times natural log 2 plus 2. So let's double check all this, make sure we did everything correctly. Looks like everything is correct. So now we just have to calculate. So we have negative 1/3 plus 1/2. So negative 1/3 plus 1/2 is going to be negative 1/6, it looks like. And we have 3 minus 2, which is 1. And so add those up and we get 5/6. And we can factor out a 2 from these natural logs. And we're left with negative natural log 3 plus natural log 2. And there's a lot of different ways that you can simplify this expression. But it's probably best just to use the calculator for the remaining part. We don't want to spend too much time on this, so let's enter this into our calculators. And we'll see what we get. So 1/2 minus 1/3 looks like that's going to be 1/6. 3 minus 2 is 1, so we get, looks like 7/6. And minus 2 natural log 3 plus 2 natural log 2. And we can do the rest on the calculator. So let's crunch the numbers. It looks like we get 1.1175 approximately. $7.9. So there you go. There's another example of one of those types of problems. So now it's time for you to try. You can get a picture of all these differentiation formulas. You're going to need those if you don't have those memorized. Get a picture of all this information. Again, this is called the disk method. We're adding up the volumes of a bunch of disks. And disks are basically just really small cylinders. Get a picture of these two problems, and I'm going to leave number 1 in the window. The formula you're going to use is volume is equal to the integral from a to b of pi r squared, because we're dealing with disks. And the cross-section area of the solid, that goes in here. and the cross section is a circle. And you're going to have to graph these equations. Now this is a cubic equation, so you're going to have to look at your parent cubic function, and you're going to have to put that 3 on the other side in order to understand how we're transforming the graph. So we have y minus 3 is equal to x cubed. That means you're going to move the parent graph up 3 units. Okay, you're expected to be able to do that. So go ahead and try. Number 2, start by graphing the area that is enclosed by the equations, and then rotate about the x-axis, and you're going to use this formula to find the volume. So try number 2. You can try to do this without graphing, but it's not really a good idea. You need to know precisely what you're doing, because when we go into more advanced problems, it's going to require you to graph these. So try number 2. When you come back, we'll do it together. Okay, we're back, and looks like that's going to be 128 pi over 7. So if you got that right, excellent. Go ahead and get a screenshot of these 2 pages here, and I want you to try this next problem. Now be aware that you're going to need differentiation formula number 9. That's this formula here. You're going to need to know that the derivative of an exponential function is the exponential function times natural log of the base of the function, because when you find the antiderivative, you're going to go in the opposite direction. You're going to divide by natural log of 3 when you find the antiderivative. Also, there's going to be a simple substitution problem, because you're going to end up with 3 to the 2x. And so technically that's a substitution. Now it's such an easy substitution problem that you don't even really need to define u and go through the whole process, but see what you can do. If you get stuck, that's okay, but try your best. Now again, the formula you're going to use is the integral from a to b of the cross-sectional area of the solid, which is a circle, pi r. The area is going to be pi r squared, and you need to graph in order to see what we're rotating about the x-axis. Try number 3. When you come back, we'll do it together. Okay, we're back. It's probably more accurate than we really need to be, but so if you just wrote maybe these decimals, that's fine. The problem doesn't specify how accurate we need to be, but that's the volume of this solid of revolution. So if you got that right, excellent. Now if you had a little trouble with this, then you need to go back and look at your exponent rules and differentiation formula number 9, and exponent rule number 8 brings these down because they're negative exponents, and so on and so forth. So now I want you to try number 4. Now be aware that this expression here is not in our library of relations, so it's not obvious what that graph is going to look like. So you need to graph that on your graphing calculator. Now you can graph it manually, but it's just going to take a while. So go ahead and try number 4. Draw your graphs, find the area that's enclosed by the graphs, rotate about the x-axis, and use this formula to find the volume of the solid of revolution. Try number 4. When you come back, we'll do it together. Okay, we're back. Now a lot of students are probably wondering, why can't I just do all this in my calculator? If you have a TI-84 Plus, you can actually do this integral in your calculator without showing any of the work. The problem is you need to know how to do this work as a calculus student. If you don't know how to do that, then you're not really learning calculus. Now, once you get your answer, you can go back to this original integral and plug in this integral into your calculator and check to make sure you did all this work correctly. That's fine, but you can't, you have to show this work. You have to show that you actually did the integral. Now, if you want to know how to do this in your TI-84 Plus, your Texas Instruments TI-84 Plus, I'll show you how to do that now. If you have a different calculator, then you're going to have to learn how to do that yourself. So on the TI-84 Plus, push the math button at the upper middle left. Then you're going to go down to number 9 where it says FNINT. Press enter, and then you can see it gives you an integral. So you can enter all that into the integral. All this stuff up here in green. Okay, so let's do this next problem together. So we're going to find the area enclosed by the graphs of these equations, and we're going to rotate about the x-axis. So let's graph to see what's going on here. So I'm going to graph the cosine function, which looks something like that. And x equals 0, that's this line here. By the way, I'm going to make this red. And x equals pi over 3, that's going to be somewhere here. Again, your graph doesn't have to be perfect. Y equals 0 is the x-axis, that's this line here, the green line. And the region bound by these graphs that we're interested in is going to be this yellow region here. Now, you may have noticed in the previous problem that the area that we started with was below the x-axis. It was this area down here. And we rotated it around, creating this solid, but even though we started with the area below the x-axis, our volume was still positive. As long as you integrate from left to right, your volume is still going to be positive. Here our area is above the x-axis, but again, integrating from left to right, our volume will be positive. So when we rotate, we're going to get a shape that looks something like this. And cross sections again are going to be circles. So we can use our formula as usual. So volume is equal to the integral from 0 to pi over 3 of pi r squared, and r is cosine x, and of course we need our pi. So there you go. We're going to take the pi out. And maybe we can change that, just showing that we're raising cosine x to the second power. You don't have to show every step that we're doing here, but so remember, this expression is exactly the same as this expression. This expression is just a faster way to write it because we don't have to use parentheses. Okay, so at this point we're stuck. And the reason that we're stuck is we cannot integrate this expression here. We don't know how. As I mentioned in previous classes, you can't just put any algebraic expression into an integral and then assume that you can find the antiderivatives. You can't find the antiderivatives of every function. And it turns out that with this expression here, we cannot find the antiderivatives. We don't know how. So we have to come up with tricks around this. And so here's a trick. We learned in previous classes that sine of a double angle is equal to 2 times sine x times cosine x. We also learned that the cosine of a double angle is equal to cosine squared x minus sine squared x. But the cosine of a double angle is also equal to 2 cosine squared x minus 1. And we also learned that cosine of a double angle is also equal to 1 minus 2 times sine squared x. So the cosine double angle formula actually has 3 identities, whereas the sine angle only has 1. Well, the one that we're going to use is this one. That one's going to be useful to us. So you might wonder, am I supposed to have that memorized? Do I have to have those double angles memorized? And the answer is yes. You need to have your trigonometric identities memorized. A lot of students don't want to hear that, but unfortunately you have to have those memorized at this point in your math curriculum. You're going to be expected to just come up with those out of the blue. And I think earlier in a class I said that I was going to show you your identities once and I wasn't going to show you them again, but I guess I lied, because I'm going to show you the identities again. And we don't use all of these identities, so don't think that you have to memorize everything on the list, but there are certain things that you're expected to use, and I'm going to show you which ones. So these are the ones you're expected to be able to use. So now what we're going to do is we're going to solve for cosine squared. So I'm going to subtract, or I'm going to add 1 to both sides of this pink equation. Then I'm going to divide both sides by 2. So what I did is I found an alternate way to write cosine squared x. Instead of writing cosine squared x, like we have up here, we can change it to cosine 2x plus 1 over 2. So the reason we did that is because this expression is going to be easier to find antiderivatives of this expression rather than this blue expression. So again, I know what you're thinking. You're thinking, that's a dirty trick. How in the world are we supposed to know to do that? Well, that's just the way that integration works. You're going to be expected to have some tricks in your bag. And trigonometry has a lot of tricks like that you need to be familiar with. So all we did was just replace this blue expression with this green expression here. So it's a lot easier to work with. So now let's see if we can find the value of this integral. Now I'm going to take this 1/2 out, make it pi over 2. A lot of students may object to that, say, no, you can't do that. But all we did was just factor out 1/2. If you multiply this expression by 1/2, you'll see that you get to this. You have a common denominator, add the two terms together. Okay, so now we're ready to find the antiderivative. Now, this is technically a u substitution. We would make 2x equal to u, but it's such an easy integral, it's an easy expression that you can really skip that if you don't want to have to do that. It's pretty easy to find the antiderivative of this in our heads. So it's going to be 1/2 sine 2x. That's the antiderivative. So that really wasn't very hard. But if you want to know why or how we can do that, you'd have to use u substitution. So if you're going to find the derivative of this expression to prove that we get back to the original green expression, then you have to use a chain rule, because we have a function inside another function. So if you find the derivative of this, the derivative of, well, using the chain rule, the derivative of the outside function is cosine. That's step number 1. We keep the inside function, that's step number 2, and then we multiply by the derivative of the inside function, and the derivative of, or the inside function is 2x, so the derivative of 2x is 2. So the 2 pops out, multiplies by the 1/2, and it makes that 1/2 disappear, so you have nothing here. That's why we know that works. Now again, if that seemed complicated to you, then you can just let 2x equal u and do a u substitution, like we learned in the previous classes. So now we're ready to proceed. So we're going to plug in 1/3 or excuse me, we're going to plug in pi over 3. Then we're going to subtract that same expression with 0 plugged in. So there you go. Okay. So it looks like we're going to get sine 2 pi over 3. So remember, pi over 3 is 60 degrees. So 2 pi over 3 is 120 degrees. So we're going to go over here. If we draw a triangle at 120 degrees, 2 pi over 3 is 120 degrees. Then we see that our reference angle is 60 degrees, and we're dealing with a 30, 60, 90 degree triangle. This side over here is negative x, and this side is positive x root 3. And the hypotenuse is 2x. So you need to know your 30, 60, 90 degree triangles and your 45, 45, 90 degree triangles. That's something else from trigonometry that you need to know. And you can review that using that information that I showed you about trigonometry. So that'll help us find the value of sine 2 pi over 3. So sine is opposite over hypotenuse, which is root 3 over 2. So we have 1/2 times root 3 over 2. And this is what we call a quadrantal angle, and that's a collapsed triangle. So when you have a collapsed triangle, you need to use your sine curve. And you see when we're at 0 degrees, the graph is just 0. Or the y value of this orange point is 0. Now if we had 90 degrees, the y value would be 1. So that's 1 there. If we had 180 degrees, the y value would be 0, because that's pi, which is equal to 180, and so on and so forth. So you need to be familiar with your radian angles and all kinds of different trigonometry that we're using here. So at this point, we can use our calculators. So we get root 3 over 4 plus pi over 3, and all that is multiplied by pi over 2, and so we get approximately 2.3251. So there you go, 2.3251. So we had to use a trick there in that problem. We had to convert cosine squared x to cosine 2x plus 1 over 2. So that's stuff's gonna come about quite a bit in the calculus curriculum. And if you thought that was a difficult integral, well, they get even more complicated than that. You have to use some really weird tricks when you go into the next course. So that's just something you're going to have to get used to, using tricks to find antiderivatives. So I want you to try number 6. Now for number 6, you're going to be using a different cosine double angle. You're going to be using this cosine double angle. So you need to be aware of that. Don't forget, you got to use that blue equation, because we cannot find the antiderivative of sine squared directly. We don't know how to do that. Now there's something about this problem that I want to show you real quick here before we do this. So I'm going to graph sine for you. So I'm kind of cheating a little bit and doing some of this problem for you. Y equals 0 and x equals pi and x equals 2 pi. Now the big question is, why do we need these vertical lines, these purple vertical lines? Because those lines are not really necessary to enclose the area. Let me move this over a little bit. This area here would be enclosed without those purple lines. Why do we need them? Well, the reason we need them is because how do you know that we're not enclosing area over here? The green horizontal line and the red graph, they enclose that area. And how do you know we're not enclosing this area? So you have to specify with those vertical lines what area you're enclosing. So we're enclosing that yellow. So I did the graph part for you. So use this formula and see what you can do. Try number 6. When you come back, we'll do it together. Okay, we're back. So it looks like we're going to have pi squared over 2. So if you got that right, good. Now these two expressions are both 0. We're dealing with quadrantal angles there. So if you draw your sine function, again, we need to use the graph, the sine graph, because these are collapsed triangles, they're quadrantal angles. So 2 pi is going to be here, and you can see that the y value of that point is 0. 4 pi is going to be here, so the y value of that point is 0. So those two expressions are 0. Now again, a lot of students would look at this and they would say, well, I don't know that. I learned it months or years ago, but I don't remember it. Well, again, calculus teachers aren't going to care if you remember it or not. They're just going to expect you to know that. So I'm giving you reminders here, but I'm just letting you know that most calculus teachers aren't going to remind you of that at all. They might do a little bit of pre-calculus review at the beginning of the course, but they're not going to help you along the way. So just be aware of that. That's the hardest thing about calculus. It's not the calculus itself, it's all the prerequisite material that you're expected to know. So if you're having a little trouble with the prerequisite material, that's normal, but the important thing for you to get straight is that it's up to you to figure it out. Your calculus teacher isn't gonna spend a lot of time helping you with that, and I know that that's not fair, but that's just the way it is. Again, I'm giving you a lot more than most calculus teachers would give you when it comes to the prerequisite material. So now we're going to go on to something called the washer method, and the washer method is really the same method as the disk method. It's just that we're finding two cross-sectional areas rather than just one cross-sectional area. They're both circles. The cross-sectional areas are both circles, but we're finding an outer circle and an inner circle, and we're going to find the, we're going to add up the volume of washers. So these shapes here. Before we were just adding up discs, but now we're going to be adding up washers like this. They're actually hollow in the middle. The discs weren't hollow, they were completely filled. So this is the disc method here, but it's not going to really make much sense until we do a practice problem. So here we have an example with the graphs. So we have the same type of problem that we did previously. The only difference is that if you look at this this region here that's bound by the graphs in question, notice that this shaded region is not up against the x-axis. So when we rotate that area about the x-axis, look what happens. We have a hollow part in the middle. This part is hollow. Well, it turns out we can still find the volume of the solid, but we have to use, again, what we call the washer method rather than the disk method. The washer method is really just the disk, using the disk method twice. So now what would this shape look like? It's kind of hard to explain, I guess. You could still consider it to be a cup if you consider the cup on its side and this orange vertical line to be the surface of a table. You still have a cup, I guess. In fact, this is even more so a cup because you can actually put liquid inside it. It's hollow on the inside, whereas the other shape wasn't really, you couldn't use that as a cup. It just had kind of a cup shape. So what we're going to do is we're going to find the volume of the shape as if it was not, as if it were not hollow. We're going to find the volume of the whole thing, but then we're going to and we're going to use the disk method, of course, to find the volume of the whole thing as if it were not hollow. But then we're going to use the disk method again to find the volume of this orange part in the middle and subtract the volume of the orange part, and that's going to give us the volume of the yellow part that's rotated around. And so we call this the washer method because when we do that, what we're really doing is finding the volume of little circular washers and adding them up. Of course, I'm not really drawing this proportionally because it's hard to draw that, but we're adding up a bunch of washers. A washer here, a washer here, and then a washer here, and a washer here. We're adding up an infinite number of volumes of washers to find the volume of that solid. So let's set up our integral. Our formula is going to look a little bit different. It's going to be the integral from a to b of the cross-section area of the bigger circles minus the cross-section area of the smaller circles. So this is the formula that we're going to use to find the volumes of washers. And so if we look at those equations, well, we're going to plug in the purple numbers 0 to 2, and you see the green graph is above the red graph, so that's where we're going to start with. Pi times r squared. So we are raising that green equation to the second power, and then we're going to subtract the cross-sectional area of the smaller, the hollow, the inner part. So we have pi times r squared. So again, this is called the washer method. And we have to make sure that this cross-sectional area is represents the bigger circles. That's these circles. And this cross-sectional area represents the smaller purple circles that are inside. They're the inner part. Okay, let's double check all this, make sure that's all right. It looks good. So now I'm going to transfer this up to the next page because obviously we don't have much room to do our work. Now again, you probably noticed that it would be really easy just to use our calculators to find the value of that integral, but unfortunately in calculus class you're not really allowed to do that. You have to show that you can do the calculus yourself. Okay, so I'm going to pull out pi because pi is a factor of this term and this term, so why not just pull it out so we don't have to keep rewriting it. And then I'm going to use FOIL on this expression, and I'm going to go through this kind of quickly because it's going to take a long time unless we go at a reasonable pace here. So it looks like that's what we're going to have in our integral. So let's double check all this, make sure we got it right, looks correct. So this is kind of a big integral to have to deal with, and you know, unfortunately in calculus sometimes you just have to deal with complicated expressions like this. You know, there's nothing we can do to really avoid it. You can try to simplify, but sometimes you just have to buckle down and do the math. So we're combining these pink expressions. 1/9 minus 1 is negative 8/9. So highlighting kind of helps us to see what we're doing sometimes. And then we get 40 over 9, it looks like. So we combine these blue expressions to get that. That expression went to there. Okay, so let's double check, make sure we got this all right. Everything looks correct. So now we can find the antiderivatives of all this stuff. So we get negative 1 over 20 x to the 5th minus 8 over 27 x to the 3rd plus I think we're going to have 14 over 18 x squared, and so on and so forth. Now thankfully one of our limits of integration is 0, so that's going to make things a lot easier for us. So now we're ready to plug in 2. I'm going to reduce that to 7 over 9. And then we're going to subtract the same thing with 0 plugged in. I'm just going to copy all that stuff. Let's see if we can make room. So we're subtracting all that stuff, and make sure to get your signs right because it's very easy to not write your signs correctly, and then you'll get the wrong answer. Okay. So again, I'm going to just go through this pretty quickly. So we get negative 32 over 20 minus 64 over 27 plus 28 over 9 plus 80 over 9, and all that stuff is going to be 0. So all this stuff turned into 0, but I forgot to change my 2's to 0's, so let me go ahead and do that. So up here we have purple 0's. Okay, so all that stuff turned into 0. So now we can simplify this a little bit more, I guess. 28 plus 80 is 108. We can reduce this to 16 over 10, which is 8 over 5. And you can do the rest with your calculator, because that's kind of a lot to have to do. So I'm going to enter this into my calculator. And times by pi, and we get 25.225 approximately. .2258. So there you go. So that was the washer method. Again, sometimes we can't avoid problems with a lot of complicated math there. Now you could get an exact answer here if you wanted to do a lot more math and combine these, but that would take a long time, and so I don't really require you to get an exact answer necessarily, but you do need to show the steps along the way. So again, that was the washer method. It's a very similar formula. So now we have the area bounded by these graphs, and again, notice that this area is not up against the x-axis, so when you rotate it, there's going to be a hollow part in the middle. So what we're going to do is we're going to find the volume of washers like this, washers that have an outer radius and an inner radius, and we're going to add up the volume of those washers. So here's the formula. And so we're going to go from pi over 6 to 5 pi over 6. And the radius of the outer part of the washer, the bigger circle, is going to be sine x. And the radius of the inner part is going to actually just be 1/2, so that makes it easy for us, because it's just a vertical, or excuse me, a horizontal line. So the volume of this part in here, that's really easy. That's just going to be the volume of the cylinder. A very simple cylinder. The height of the cylinder is this length, and the radius is this length here, and so on and so forth. So you could just use your basic volume formula for that, but we're going to use this formula so we can get more familiar with it. So I'm going to factor out pi. Again, you don't have to factor it out, but it just makes it easier so you don't have to keep rewriting pi. And we have sine squared x minus 1/4. So all we have to do is find the value of that integral, and we're done. Problem is, we have sine squared. We don't know what to do with that. We can't integrate that. So remember, when we have sine squared, we use this identity to help us. And what we do is we solve for sine squared. So we're going to change the form of the expression in the integral to help us integrate. So we have 1 minus cosine 2x over 2. So we're going to replace this expression here with that. So we get 1 minus cosine 2x over 2 minus 1/4. Now, to make things easier, I'm going to factor out 2. You don't have to factor out 2, but it makes it a lot easier to integrate. Now I'm going to be left with 1 minus cosine 2x minus 1/2. Now, if you want to know why that works, just multiply 1/2 back into these, and you'll get this expression up here. So now we can combine these numbers here. So I'm going to do that. And we get, looks like 1/2 minus cosine 2x. So we've simplified the expression as much as we can. Let's move up here so we have more room. So this is a lot of busy math, really, and the busyness of this math is not really the point of these problems. The point is just to know how to set up the integral. I guess we're ready to find the antiderivative. So we're going to have 1/2 x minus 1/2 sine 2x from pi over 6 to 5 pi over 6. Now again, you can use a u substitution here, but that takes time to use a u substitution, and it's such an easy u substitution that you can really almost do it in your head. So if you find the derivative of this, to see if we get back to this, you find the derivative of the outside function, you keep the inside function, and you multiply by the derivative of the inside function, which is 2, and that multiplies by the 1/2 and makes it go away. Okay, so we're going to plug in 5 pi over 6. And then we're going to subtract the same expression with pi over 6 plugged in. And you have to change the signs when you subtract. You can show that, but it's going to get kind of tedious if you have to show every single detail of this. This is just basic algebra. Okay, so it looks like we have 5 pi over 12 minus 1/2 times sine 5 pi over 3. Now that's a special angle, so we can calculate that. Minus pi over 12 plus 1/2 sine pi over 3. So pi over 3 is another special angle, so we can calculate that. So 5 pi over 12 minus 1 pi over 12 is 4 pi over 12, which is pi over 3. Again, that's just basic mathematics. Now to calculate these, you need basic trigonometry. So we can go over here. 5 pi over 3, pi is 180 degrees, divided by 3 is 60 degrees, times 5 is 300 degrees. Or you can think of this as pi over 3 being 60 degrees, multiplied by 5, you get 300. Or you can just use the basic conversion factor, which is 180 over pi. The pi's cancel out. You end up with 300 degrees, but you need to be familiar with, radian units. So 300 degrees, that would take us all the way to here. We see our reference angle is going to be 60 degrees. So this side is negative x root 3, this side is x, this side is 2x. It's a 30, 60, 90 degree triangle. Are you expected to know 30, 60, 90 degree triangles? Are you expected to know everything about them? And the answer is yes. That's something you have to memorize. Sine is opposite over hypotenuse, so that's going to be negative root 3 over 2. And then you're going to do the same thing in the first quadrant for pi over 3. Pi over 3 is 60 degrees. So we have positive root 3 over 2. Okay, so simplifying, looks like we're going to have pi over 3, and then we're going to have plus root 3 over 2, it looks like. So you could come up with an exact answer if you wanted to, but that's always preferred. But you can enter it in the calculator also, and you're going to get approximately 3. Even if you come up with an exact answer, it's not going to be very, very pretty. So that is the washer method. So let's do a couple more of these problems before you try one on your own. Now we're entering a problem set here, so we don't have pictures drawn. And with this problem, we don't have any bounds. So let's see what's going on here. Root x, that's going to look something like this. And x equals y, that's going to look something like this. So our area that we're considering is this area here, but we don't know the bounds, the limits of integration. That's going to be given by these purple points, but we don't know what those purple points are. So sometimes you have to do some algebra. So we're going to set y equal to y, set those y values equal to each other, square both sides, subtract x from both sides, and then we're going to factor a GCF, which is x, and then we can see the only x value that would make those y values equal, the only x values are 0 or x equals 1, which makes sense because one of our x values should be 0. That's where our intersections occur. So this point here is, if you plug in 0 for x, or if you plug in 1 for x, you get 1. So that's 1, 1. And this point here is 0, 0. Now we're going to rotate that about the x-axis. So we're going to get something that looks like this. My graph may not be exact here. In fact, it's not exact at all. Your picture doesn't have to be perfect, it just has to give you an idea of what we're rotating. So when we rotate around, we're going to get this shape here, but notice that this part there's nothing there, it's hollow. That's why we have to add up the volumes of washers. We're adding up the volumes of washers rather than adding up the volumes of discs. Okay, so volume is equal to the integral from 0 to 1. And again, we got that from those numbers up there. 0 to 1 of pi times the radius of the bigger disk. And that's going to be root x. So pi r squared minus pi r squared, and r for the second, for the smaller disks is going to be x. So this is going to be a much easier integral to work with. So we just have pi times x minus pi times x squared. And I'm going to go ahead and take that pi out. So we have x minus x squared dx. It's a much easier integral to work with. So our antiderivative is 1/2 x squared minus 1/3 x cubed, 0 to 1. So we have 1/2 1 squared minus 1/3 1 cubed minus 1/2 0 squared plus 1/3 0 cubed. So we have 1/2 minus 1/3 minus 0. Doing all the math with that, we end up with, looks like pi over 6. So there's another example where we used the washer method. So let's try one more of these before you try one on your own. Again, we're using the same formula. And maybe I should write that formula over here of pi r1 squared minus pi r2 squared dx. Okay, so I want you to try the next problem. You can get a picture of example 3 and also example 4. So attempt number 8, but be aware that this cosine double angle formula will be very useful. You're going to have a cosine squared expression, and you're going to have a sine squared expression that appears in your integral, and you can combine those to get this this cosine double angle. That'll make it easier for you to deal with the integral. You don't have to use that. You can use other formulas, but this formula is going to be the easiest to use. So please use this formula when you see cosine squared and sine squared subtracted from each other, because it's just going to make it a lot easier for you to do the integral. So try number 8. Draw your graphs, rotate the enclosed area about the x-axis, and use this formula, which employs the washer method. Try number 8. When you come back, we'll do it together. Okay, we're back. Okay, so that is the answer. If you got that one right, excellent. Again, when you see the cosine squared and the sine squared and they're subtracted, whoops, I forgot to put an x in there. If they're subtracted, then you can use that formula to simplify things. If you don't use that formula, then, well, you have to use the other cosine double angle formulas. So you can take a picture of these problems, and I want you to try number 9. So graph the equations, rotate the enclosed area about the x-axis, and use your special formula. Remember, this is the formula. This is the washer method. So try number 9. When you come back, we'll do it together. Okay, we're back. So the final answer is exactly 44 pi. So if you got that right, excellent. So I want you to try number 10, but notice that we don't have any of these purple equations here that helps us to find the limits of integration. With this equation, you have to set these, or with this problem, you have to set these equations equal to each other to find where the intersection is. So be aware of that. Try number 10. When you come back, we'll do it together. All right, we're back. Looks like 96 pi over 5. So if you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And number 2. And number 3. And number 4. And number 5. And number 6. And number 7. And number 8. And number 9. And number 10, but don't go before you get your homework. Here's the homework. Remember, the homework must be done completely and correctly, so here's screenshot number 1 and number 2 and number 3 and 4 and 5. But don't go before you get the answers. It's not enough just to attempt the homework, it must be done correctly. So here's the answers. So get that homework done, and I'll look forward to seeing you in the next class.